Okay, so I'm going to show you how to solve these problems for ideal mechanical advantage, actual mechanical advantage, and efficiency. So I'm taking three of the questions out of the sheet that you have, and you can kind of see how I did them. Just know that number 13 here, this one is a bolded question on your sheet, which means it's kind of higher level. So don't feel like you have to do any of those bolded ones, but I wanted to at least show you how to solve those. So a mover uses a ramp to load a crate of nails onto a truck. The crate, which must be lifted 1.4 meters. So that's this right here. It's the distance it has to be lifted up is 1.4 meters. From the street to the bed of the truck, that is pushed along the length of the ramp, which is 4.6 meters long. So that's from here to here. That's the distance it has to be pushed along. But again, it's only going up 1.4 meters. Okay. Friction between the ramp and the crate can be ignored for this problem. What is the mechanical advantage of the ramp? So kind of looking up here, you're given two formulas, ideal and actual. The only one that has distances involved is this one for ideal mechanical advantage, the distance of the input force divided by the distance of the output force. So you're going to put your force into this ramp in this direction, and you're going to do it for 4.6 meters. That is your input force, the distance of your input force. And what's the ramp going to do for you? It's going to lift the crate 1.4 meters. This is your output distance. Okay, so the crate will be lifted up 1.4 meters, but you're going to have to push it for 4.6 meters. So the way to solve this problem is you're going to plug in 4.6 for the distance of the input force and divide that by 1.4. So 4.6 divided by 1.4. And if you do that out, you're going to get 3.3. Okay. For the next question, a lever does 765 joules of work, and the person using the lever applies 890 joules of work. So the person is going to push down on the lever here, and they are going to move it downward, the force over a distance, and that's going to be 890 joules. The lever is not going to do the 890 joules because in this case, we're going to think that there is actually friction involved. So the output is going to be less, which is 765 joules. So what is the efficiency? So there are two ways to figure out the efficiency. Since we don't know what the ideal mechanical advantage or the actual mechanical advantage are, we're going to use this one right here, work out divided by work in times 100. Well, the workout is what the lever does. The lever does 765 joules of work. And the work in is what was applied, and that was 890 joules. That's a 9, I promise. And so if we do 765 divided by 890, we're going to get about 0.86, which we then multiply times 100, which gives us 86% efficiency. Okay. And then we come down to our last one down here. Clyde, a stubborn 350. I'm going to move this over so I can give myself some room. Sorry about that. Clyde, a stubborn 3,500 Newton mule, refuses to walk into the horse trailer. So Farmer Brown must drag him up a 5-meter ramp, which stands 0.5 meters above the ground. So let's do that first. That means this part is 0.5 meters, the part that the ramp is going to lift old Clyde. The farmer is going to have to drag him this entire distance, which is 5 meters. So if we come back up here and look at the formula, the ideal mechanical advantage is the distance of the input divided by the distance of the output. The input is 5 meters. The output is 0.5 meters. And so that's going to give us a mechanical advantage, an ideal mechanical advantage of 10. So Farmer Brown is going to exert a force of 450 newtons to lift Clyde. Now, Clyde is going to move up. Clyde is a 3,500 Newton mule, and that is going to be the load or the output force. So the output force, Clyde in this case, is 3,500 newtons. So I'm going to do 3,500 newtons divided by the input force, the force the farmer pushes with, which is 450 newtons. And if I do that out, I'm going to get approximately 7.78. It's actually 7.7777, but you get the idea. So then it's looking for the efficiency of the ramp. So the efficiency is again going to be the actual mechanical advantage, in this case 7.78, divided by the ideal mechanical advantage, which is 10, and all that times 100. And if I do that out, I'm going to get 77.8%. I already multiplied it by the 100 to get my percent.